Welcome to Math with Professor V. In this video, we're going to learn more about how to evaluate double integrals in polar coordinates. This is part 2. So if you haven't watched the introductory video lecture on double integrals in polar, I'll link it in the description and in the top right here. I'm not going to go into too much of the background concepts. I'm just going to work through and crank out a bunch more examples since I had requests to do so on this topic, okay? Namely, I'm just going to do the entire homework assignment that I give my Calc 3 class, pretty much. Now, I want you to notice nowhere in the directions does it say graph, but we're going to graph. There's just no way around it, okay? Especially when you're first starting these, you have to graph the two-dimensional region, the base region that you're going to be integrating in the XY plane. That's how you set these up. So here we go. Evaluate the integral by converting to polar coordinates. So we have double integral over some region D, x squared y dA, and we know dA is going to be polar, where D is the top half of the disk with center at the origin and radius 5. Okay, first things first, you betcha, we're graphing. So we have just top half of a disk centered at the origin, radius 5. So we're just in 2D. Let me draw a disk. That looks about right. Centered at the origin and the radius is 5. Now, this region D is only the top half of the disk. So only this portion here. Okay, great. So now what I need to do is figure out what limits of integration would correspond to this region D right here. Now remember, when we're in polar, dA is r dr d theta. I explain why that is the case in the introductory video lecture. So what we need to do is figure out what our limits of integration are for r and for theta. Now always remember, the outermost limits need to be constants, and typically d theta is last. So those theta limits should be constants. On occasion, r will be a function of theta. A lot of the time in these beginning problems, r is also just a bunch of constants, okay? So here's the idea. To figure out the bounds for theta, you simply look and think to yourself, what angle, right? What values of theta would bound the region D that lives in quadrants 1 and 2? Notice here, this is where theta equals 0. We're using our standard orientation for measuring theta, and we go counterclockwise up until this would be at pi. Theta equals pi. So the limits for theta are from 0 to pi. Now the limits for r when you're in polar, here's the easiest, best way to do it. You start at the origin and you draw a ray outward, always outward, and it could be in any direction, okay? Where that ray starts in the region is the lower bound, and where it exits is the upper bound. So what do I mean by that? Well, from the origin onward, this is entirely in the region D. So the lower limit for r will start at 0, and it will end here, while r is consistently 5 for this entire circle. A circle radius 5 has the equation r equals 5 in polar. So the limits for r are from 0 to 5. Good? And you can draw that in any direction. So then now let's set up our integral. I'll put theta on the very outside. So we're going to go 0 to pi. Those are my limits for theta. Now limits for r, 0 to 5. Then we have to switch x squared y to be in terms of polar coordinates. So x is r cosine theta. All of that gets squared. Y is r sine theta. And then dA is r dr d theta. Good? Okay. Now we have a fabulous theorem that tells us that when our limits of integration are all constants and the integrand is a product of functions of r and theta, or it could be x and y, depending on, what region you're integrating over, we can split this into a product of two integrals, each of a single variable. So what does that mean? Well, I can break up all the thetas and the r's basically, and then be back in like Calc 1. Do a relaxing little integral. So 0 to pi are the limits for theta, right? So I can say 0 to pi times integral right here, cosine squared theta, sine theta, d theta. Evaluate that guy by itself. And then I can do another integral from 0 to 5. I have 1, 2, 3, 4 powers of r to the 4th, dr. Okay, you can't do that unless these are all constants, and then the integrand is a product of functions exclusively of r, a function of r times a function of theta. If there's any like addition or mixing, you can't do it. Okay, I'll show you some where we can't do it coming up. Okay, from here, since I have just this one odd term out, sine theta, we would let u be cosine theta, right? Then du would be negative sine theta d theta. I'm just going to do the u sub in my head because I don't feel like switching these limits of integration. So negative u squared, antiderivative would be negative 1/3 u cubed. So this is going to be negative 1/3 cosine cubed theta, evaluated from 0 to pi, okay, times, and then over here we're going to have, 1/5 r to the 5th, and then this is evaluated 0 to 5. Oops, that should be like a little bracket. Okay, good. So then this is negative 1/3 cosine of pi, that's negative 1, cubed, it's still negative 1, minus, that'll just be 1. Very good. And then 5 to the 5th divided by 5 is now 5 to the 4th. So this ends up being positive 2/3 times 625, which is 1250 over 3. Okay, good. I'm going to spend most of the time in the video explaining the setup of the integrals, and then I'll just kind of breeze through actually evaluating them so this isn't too lengthy. And I feel like the hardest part for most students at this point is just the setup anyhow. Okay, good. Let's look at more examples. Okay, you'll get better at it just the more experience you have. So let's do that now. Double integral over r of sine of x squared plus y squared dA, where r is the region in the first quadrant between the circles with center the origin and radii 1 and 3. Okay, so we're just looking at the first quadrant. Make sure this is all nice and straight. And we want circles with radii 1 and 3. And here they are. 1, I'm just going to draw like this little piece. And then here's radius 3. And so R is this region in here. Okay, good. So we need to figure out limits for theta and limits for R. Well, look here, theta goes from 0 all the way to, was it up there at the top? Pi over 2, yes? Okay, so from 0 to pi over 2. And then what about the limits for R? So always start at the origin, draw a ray outward. This will be the lower bound where that ray enters the region R. This will be the upper bound where the ray exits the region R. So that goes from R equals 1 to 3. 1 to 3. 1 to 3. Good. Okay. Then now we have double integral over R sine of x squared plus y squared dA, and we've decided we're going polar, so theta on the outside, 0 to pi over 2, 1 to 3 next, sine of, now x squared plus y squared is just r squared in polar, and dA is r dr d theta. Good? Okay, perfect. Now, in this case, what we're going to do is we can still break it up. We certainly can. So I can write this as 0 to pi over 2. There's no thetas, so it's just d theta. And then I'm going to show you a snazzy little shortcut right now. And then we have 1 to 3 r times sine of r squared, dr. Are you all right? Okay, now look at this. When there's no variable, there's no theta, the antiderivative would just be theta, evaluated from 0 to pi over 2, which is just going to be pi over 2 minus 0, right? Which is just basically upper limit minus lower limit. So I'm totally fine. I tell my students, when you notice that, you can just slap on a pi over 2 and move on with your life. And in fact, I don't even need them to write this part out. As soon as you notice, do a quick scan. I don't see thetas here. Here's d theta, 0 to pi over 2. Get rid of that guy. Get rid of this integral here. and just add pi over 2. Boom. It's going to happen often, okay? Then from here, what would you do? You're going to do another u sub. U would be r squared. Du would be 2r dr. So I'm going to have a 1/2 when I take the antiderivative, and then add a negative. I'm going to do it all at once. Really aggressive, I know, guys. So negative 1/2 cosine of r squared, and then that gets evaluated from 1 to 3. So this is going to be negative pi over 4 cosine of 9 minus cosine of 1. Neither of those are nice values that we know from the unit circle. I would just distribute the negative and switch the order of subtraction. Pi over 4 times cosine of 1 minus cosine of 9. And that's it. Box it with pride and move on with your life, as I like to say. Okay, good. All right, don't worry, I got plenty more. I'm pretty much doing the whole homework assignment. So if you're in my Calc 3 class, you're welcome. Okay, double integral over d, e to the negative x squared minus y squared dA, where d is the region bounded by the semicircle x equals square root 4 minus y squared and the y-axis. Now, had they not told me this was a semicircle, we should be able to figure that out. You'd get the full circle if you squared both sides. So x squared equals 4 minus y squared, right? If I square both sides, and then x squared plus y squared equals 4. Yep, that's a circle with radius 2. Now, since we've solved for it in terms of x and we're using the positive radical, this is just going to be the right half. When you solve for y in terms of x, you get the upper half and lower half of the circle. When you solve for x in terms of y, right half, left half, okay? So it's bounded by that semicircle and the y-axis. Okay, so it's the entire right half of the circle, it seems. Radius is 2. You got that? Okay, good. 1, 2, 1, 2. I'm just going to draw it by hand. Sometimes that autocorrect, it really just gets in the way, you know? Okay, right half of the circle. Ba-dum, ba-dum. Here we go. Lovely. So we got to figure out limits for theta and r. Theta, remember, measure with standard orientation, going counterclockwise. This is at negative pi over 2 all the way up to positive pi over 2. Now what about r? I told you start at the origin, draw a ray going outward in any direction your heart desires. It's going to go from 0 to 2. 0 to 2. Good? Perfect. Okay, here we go. So our integral is going to go negative pi over 2 to pi over 2, 0 to 2, e to the, now be careful, this is negative x squared plus y squared, which in polar is negative r squared, right? So e to the negative r squared, and then dA is r dr d theta. Thank goodness we have this r, because then we can u sub. Otherwise, we couldn't evaluate this integral. Okay, are you ready? We're going to do the shortcut. You see how there's no thetas here? So get rid of d theta, get rid of this outermost integral. You're just going to do pi over 2 minus negative pi over 2, which is just pi, exactly. And then you still have 0 to 2, e to the negative r squared r dr. Good? All right, so we've got pi. Yep, I'm doing it in my head. So let u be r squared or negative r squared, whatever. You're just going to pick up a 1/2 because I only have r, not 2r dr. So negative 1/2. I already am doing the antiderivative, guys. Okay. And then this will be negative pi over 2 times e to the negative 4th minus e to the 0, which is 1. And then again, reverse the order of subtraction. Get rid of that minus sign. Pi over 2 times 1 minus e to the negative 4th. Good? See, they're not so bad. They're not so bad. They're going to get spicier, but I'm here for you. And then you'll be fine. You'll be totally fine. Okay, double integral over r of arctan of y over x dA, where r is the region in the xy plane, bounded between 1 and 4, x squared plus y squared is between 1 and 4, and ooh, y is greater than or equal to 0 and less than or equal to x. Okay, so first let's draw this restriction. that means we have the area bounded between the two circles whose radii are 1 and 2 respectively. So let me just get a couple circles on here. I'll say that's radius 1. Copy, paste, stretch her out. I mean, that looks fabulous. Wow, wow, wow. Okay, so this is radius 2, this is radius 1. So we have this region between them. Looks like a donut. You know, comment in the comments, what's your favorite kind of donut? I still am somewhat of a child. I like the vanilla with rainbow sprinkles. Okay, and then also y greater than or equal to 0, less than or equal to x. So basically the line y equals x also bounds the region, but y has to be greater than or equal to 0. And I know y equals x goes through here like this, but y has to be above the x-axis. So we're just going to be looking at this little piece here in quadrant 1. So say this is the line y equals x right here. And then this is y equals 0, right? So really the region that we're looking at is just this piece right here. Just this piece. Are we okay? All right, good, good, good. Fabulous. So let's see, what are the bounds now for theta and for r? This is a little different. Okay, so theta, clearly it starts at 0. At what angle does that line y equals x come through and cut the region? What is this angle right here? Well, I know it's 45 degrees. It's pi over 4. If you're not familiar with that, the slope would give you what tangent of theta is. So since the slope of that line is 1, tangent of theta is 1. That happens at pi over 4, should you not know that off the top of your head. So theta goes from 0 to pi over 4. R, use your same little trick I showed you. Draw that ray from the origin outwards. Starts at 1, ends at 2. Good? That's all there is to it, 1 to 2. Okay, here we go. Let's set up this integral. So 0 to pi over 4, 1 to 2, arctan. Now we got to go polar. So y is r sine theta. X is r cosine theta. And dA is r dr d theta. Okay, okay, okay. These r's cancel. Now we have 0 to pi over 4, 1 to 2, arctan of sine theta over cosine theta is tan theta, r dr d theta. Do you see that? Oh. So then basically, this is just going to give me theta when I simplify. That's nice. 0 to pi over 4, 1 to 2, theta times r dr d theta. What a nice problem. Then we can split these up, okay? We can split them up. 0 to pi over 4, theta d theta, and then 1 to 2, r dr. Okay, very good. So then this is going to give us 1/2 theta squared, evaluated from 0 to pi over 4, times 1/2 r squared, evaluated from 1 to 2. So what is this going to be? I wanted to take these guys out together. So we've got a 1/4 times pi squared over 16 minus 0 times 4 minus 1. So that's going to be 3 pi squared over 64. All right. These are never like the craziest integrals. Maybe once in a while you'll have to do some fancy maneuver, but for the most part, they're fairly tame. Haven't they been? Okay. Use a double integral to find the area of the region. So when you're using a double integral to find area, you don't have a function that you're integrating. You just evaluate double integral dA. That would give you area. Area of D. Okay? And we're finding the area inside one loop of the rows r equals cosine 3 theta. I have a whole video dedicated on graphing polar roses And then also finding their area, but for a Calc 2 student, not using a double integral. But if you struggle just with the graphing of the polar rows, that video has your name all over it, okay? Anyways, I'm just gonna jump in and act like you know how to graph a polar rows. We only need one loop, so I'm gonna graph only one loop, and I wanna figure out how long it takes for one loop to get traced out. Namely, I want to know how long it takes for R to start at 0 and then come back to 0. That's how you know a loop got traced out. R goes from 0 back to 0. So you just set the function equal to 0 and solve. Cosine 3 theta is 0. So let's see, cosine is 0 at pi over 2 plus pi k, where k is some integer. And then that means theta equals pi over 6 plus pi over 3k. All right, so this pi over 3 right here tells me every pi over 3 petal is traced out. And we can start at pi over 6, and then another one will get traced out, pi over 3 added or subtracted from it. Okay, so I think the easiest thing to do, I'll draw one petal. Instead of doing pi over 6 plus pi over 3, I'm going to do pi over 6 minus pi over 3. Okay, and pi over 6 minus pi over 3 is negative pi over 6. So one petal will get traced out from negative pi over 6 to positive pi over 6. Remember, this is a value at which R is 0. And then it's 0 again every pi over 3. So I could add pi over 3 this way, or I could subtract pi over 3 from it. I think this will just give us a nicer picture. Okay, the length of the petal is the coefficient on the trig function, which is just 1. So the longest the petal is going to be is 1. Okay, so it's just going to be something cute like this. Oh, I love it. Okay, so we want the area of that little petal. Okay, so we need limits for theta and R. Well, hopefully you could see theta is going to go from negative pi over 6 to pi over 6. And then limits for R. So start at the origin, draw a ray outward. Start at the origin, draw a ray outward. Where it starts is the lower limit, where it exits the region is the upper limit. So it starts at 0 and it exits at the petal, not at some constant. This is not a circle like last time. It's not always exiting at 1. See, it's shorter here, longer, 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 longer. So it's exiting at the petal of the rose, the leaf of the rose, the loop of the rose, whatever. It's exiting at cosine 3 theta. Ooh, okay. Function of theta, not a constant this time. It's okay, we got it. So here we go. Let's set up our integral. Area is going to be negative pi over 6 to pi over 6, 0 to cosine 3 theta, and then we don't have a function, we just have dA, which is r dr d theta. Okay, so these are my limits here for r. I can't break this up like we did the previous ones because notice this is not a constant, okay? So we just have to evaluate the iterated integral. So here we go. We've got negative pi over 6 to pi over 6. Antiderivative of r is 1/2 r squared. Evaluate from 0 to cosine 3 theta and then d theta. Do you recognize this? 1/2 r squared d theta? Yeah, this was the formula you used for polar area when you were a Calc 2 student before you learned double integrals. All coming full circle, I hope. Okay, let me take the 1/2 out. Negative pi over 6 to pi over 6. And then this is going to be cosine squared 3 theta d theta. Now, yes, you most certainly can double this and go from 0 to pi over 6. Wouldn't that be just a slick thing to do? So no more 1/2. Let's go 0 to pi over 6. And then we've got cosine squared 3 theta d theta. And then you got to replace that with your half angle. So that's going to be, let me take the 1/2 out. I like to put the constants outside. 0 to pi over 6. This is going to be 1 plus cosine. Now double the argument. So doubling 3 theta makes it 6 theta d theta. Fabulous. We're so good at this. Okay, so 1/2 antiderivative of 1 is theta. It's going to be 1/6 sine 6 theta, evaluated from 0 to pi over 6, and then you get pi over 12. I won't bore you with the details. I think we worked through the trickiest part of it together. Good? Okay, here we go. More. Yes, of course. No one got good at this by doing 3 problems and never thinking about it again. You have to tell yourself that. Like right now, they're no big deal for me. When I first learned them, I was traumatized, you know? But you too can evaluate these double integrals with ease. You just got to put in the work. It won't happen by accident. I'll tell you a story at the end about bodybuilding that has to do with that too. Okay. Find the area of the region inside the circle, x minus 1 squared plus y squared, and outside the circle, x squared plus y squared equals 1. Okay, we got to express both of these in terms of polar equations. This one's probably easy, right? It's r squared equals 1, which is the same as r equals 1. This one you may not know off the top of your head. I know a shortcut for it. I'll show you the long way first, and then I'll show you the shortcut, okay? If we were to expand, it would be x squared minus 2x plus 1 plus y squared is 1. So the 1 cancels out. And then x squared plus y squared in polar is r squared minus 2r cosine theta is 0, right? Which is r squared equals 2r cosine theta, which is r equals 2 cosine theta. Okay, I knew that without even doing any of that work, and I'll show you how, okay? Because this situation is going to come up a lot in this class. The circle has radius 1, yes? The radius is 1. It's just not centered at the origin. The center is at 1, 0. So we've got 2 circles with the same radius. It's just their centers are at different places. So 1 is centered at the origin. Scoot up just a wee bit. Okay, perfect. And then the other one is centered at 1, 0. Beautiful. Okay. Now here's the shortcut. Here's the shortcut. When you have a circle, x equals 2a cosine theta, like this, that means it's centered on the x-axis. And the radius is a. Cosine theta tells you centers on the x-axis. If it's sine theta, then the center is on, you betcha, the y-axis. And the radius is a again. So this constant is always the diameter, or double the radius. So as soon as I looked at this, I said, the radius is 1 and it's centered on the x-axis at 1, 0. I just jumped straight to there, 2a cosine theta. You can do the same, because like who wants to FOIL if you don't have to? Okay, read carefully. Everyone gets confused. Inside the circle, inside this one, but outside this one. Okay, so it's this piece here. It's this. Shall I erase the yellow? I think so. Because we don't want this part. Okay? That's the region. That's the region. Okay. So to find my limits for theta, you know what I got to find, people? Where do they intersect? I need to know where that's happening. I need it. Okay. So we're going to set r equals 1 equal to r equals 2 cosine theta. I need to find the intersection immediately. Again, do you notice no one told me to graph? Oh, but you have to. No one should tell you to graph. You just do it, okay? Otherwise, how would you ever figure any of this out? No. 2 cosine theta is 1. That means cosine theta is 1/2. When is cosine theta 1/2? At negative pi over 3 and at pi over 3. Okay, so that's where this is. That's where this is. Yay, now we know that. So those are my limits for theta. Negative pi over 3 to pi over 3. Now what about my limits for r? Told you, draw that ray going outward. Draw the ray going outward. Where it starts is the lower limit. Where it exits the region is the upper limit. It starts at the circle centered at the origin, whose equation is r equals 1. So it starts at 1, and it stops at the circle centered at 1, 0, whose equation is r equals 2 cosine theta. So it stops at 2 cosine theta. Good? Look at us. We are so profesh. Okay, so the area is going to be integral negative pi over 3 to pi over 3, 1 to 2 cosine theta, and then we don't have a function. It's just dA. So r dr d theta. Again, yes, please double. Go from 0 to pi over 3. So 2, 0 to pi over 3. Let me take the antiderivative of r. It's 1/2 r squared, and we're going to evaluate from 2 cosine theta to 1, and then I have a d theta. Okay, this cancels with this. Now I have integral 0 to pi over 3. 2 cosine theta squared would be 4 cosine squared theta minus 1 is my lower limit, d theta. Okay, perfect. Now again, we're going to use our half angle identity. So 0 to pi over 3, that's 4 times 1/2 times 1 plus cosine 2 theta minus 1 d theta. And then you should be able to handle this. So yada, 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 it's pi over 3 plus rad 3 over 2. Okay? Very good. Good, good. I really just want to emphasize the setup because at this point, these should be integrals that you can handle. Okay. Use polar coordinates to find the volume of the given solid. So now we have a solid. So what we're going to do is if we have volume, remember that's double integral over some region D, and then you need a function dA. That would give you volume. I've explained this to my classes before. Like if back in Calc 1, okay, area was integral a to b f of x dx. Area is two-dimensional. And the way to figure that out is one integral sign gives you one dimension, and then this will give you a second dimension. We just did a bunch of areas in polar where we had a double integral over d, no function, and then dA. This is also 2d, one integral, two dimensions, but there was no function. There was no function to give us a third dimension. So then if you want volume, you would have double integral over d. You'd need some function and then dA. This would give you three dimensions, 1, 2, and then the function. That's 3D. Another way you can get volume, which you'll learn soon, hopefully, triple integral over E, usually we call it dV. There's no function. This would also give you a volume. Here's 1, 2, 3, and then there's no function, so no added dimension. If you add a function, then this would represent some four-dimensional quantity, which we'll talk about later, okay? Hopefully that clears it up. I thought that was pretty solid. Anyways, again, no one's telling us to graph, but we will. We want the volume under the paraboloid, z equals x squared plus y squared, above this disk. Now I can see very clearly the paraboloid and the disk will intersect when z is 25. Yes, I don't even have to write that out, hopefully. Okay, let's first draw the base region, and then we will draw, indeed, the three-dimensional region. Why not? We can handle it. Here's x, here's y. X squared plus y squared less than or equal to 25. This tells me the region D. If we're calling it D, you could call it R, doesn't really matter. Circle, radius is 5. Very good. Radius is 5. This is the region D. Let's slap some labels on there so we feel good about ourselves. Now let's draw the paraboloid. And it's opening up along the z-axis. And it's going to intersect, right? It'll be bounded when z is 25. So here's 5, 5. It need not be to scale. Don't fret, children. Here. And then if you project down, Here's D that we drew over there. So this is the base region over which we're integrating. That's right there, okay? But this time I want the solid that's under the paraboloid, okay? So it's gonna look kind of like a cylinder with the inside scooped out, okay? It's underneath the paraboloid. It's the outer part. Good? Okay, so first let's figure out the limits for D, the base region over which we're going to integrate, and then the function hopefully is not too difficult. The function is going to be the height of the solid. Okay, we're going to integrate in polar, so we need limits for theta and r. Notice this time we're going all the way around, so theta is going to go from 0 to 2 pi, and then similarly r, 0 to 5, right? 0 to 5. Now the solid is bounded below by z equals 0 and bounded above by the paraboloid. You can do the same little trick to figure out the bounds for the solid that we did here for the ray. You just know that the height of the solid is in the z direction. So you can draw starting at the xy plane a ray and have it go upward. It starts when z is 0 and it exits at the paraboloid, okay? So the height, the function is just going to be the paraboloid x squared plus y squared, which is r squared in polar. Okay, I think we're ready, people. So volume's going to be integral 0 to 2 pi, 0 to 5, r squared, r dr d theta. Can we split this up? We certainly can. In fact, let's use the ultimate shortcut. There's no thetas. So get rid of the d theta, slap on a 2 pi minus 0, right? Then you just have 0 to 5 r cubed dr, which is going to be 2 pi divided by 4 r to the 4th from 0 to 5. And this is going to give me 625 pi over 2. Very nice, very nice. We love it so much. Okay, moving on. Again, we want volume below, there was something on my iPad. Okay, below the plane, 2x plus y plus z is 4, and then above the disk, x squared plus y squared is less than or equal to 1. In this case, I know the height is just going to be given by the plane, and this is the base region that I'm integrating over. So I do need to solve for z in terms of x and y. So z is 4 minus 2x minus y, which in polar is 4 minus 2r cosine theta minus y is r sine theta. This is pretty easy. I would say maybe that's one scenario you don't have to graph. You're like, it's a circle for crying out loud, Professor V. Centered at the origin, radius 1, the whole inside. I think I can figure out the bounds for theta and r without graphing. And you know what I would say to you? You're right. Live your best life. You don't need to draw this circle just this once. If you're tired, don't do it. But I'm going to do it. Theta goes 0 to 2 pi, r goes 0 to 1. Okay, we're ready. So volume is going to be 0 to 2 pi, 0 to 1. Height is given by 4 minus 2r cosine theta minus r sine theta. And then dA is r dr d theta. You know what? The setup was easy, but this integral is kind of a pain. So there you go. We're going to distribute the r through, and then we'll integrate. No shortcuts can be taken, sadly. I'm so sorry. 0 to 2 pi, 0 to 1. 4r minus 2r squared cosine theta minus r squared sine theta dr d theta. So first, take the antiderivative with respect to r. So 0 to 2 pi, this is going to be 2r squared minus 2/3 r cubed. Yes, cosine theta is just a constant for now. Minus 1/3 r cubed sine theta. And then this gets evaluated from 0 to 1. And then d theta. Okay. Could be worse. Just tell yourself that whenever you're like, oh my God, this is so tedious. Just go, it could be worse. We could be doing boomerang integrals with secant cubed or something. 2 minus 2/3 cosine theta minus, I already feel better. It's not that bad. We were being dramatic. My apologies. Okay, here we go. 2 theta minus, this will be 2/3 sine theta plus, yeah, 1/3, keep your wits about you, cosine theta, 0 to 2 pi, and then plug in those limits of integration, yada, 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 it's 4 pi. Okay, perfect. Good, good. I have 1, 2, 3, 4, I think 5 more. Should we do a part 2? I don't know, I'm on a roll. Okay, sphere of radius A. You might be like, they didn't give me enough information. I'm quite frightened, Professor V. No, you're fine. You're totally fine. Sphere of radius A, let's draw it. This will be especially exciting because we will derive the formula for the volume of a sphere. What else could you ask for? Do I want more over here? Yeah, why not? Okay. A, the whole thing. So actually we need to go down there to negative A, etc. And then here, excuse my wobbly little sphere. Okay, we got the idea. I don't want to make it too messy. I have to say, as nice as, technology is, there's nothing like the grip and shading you get with like good old paper and pencil, Okay, so what does the base region look like over which we're integrating? Because this whole section's been polar. We're going to do double integral over the xy plane as a polar region. It's just a circle, radius A, isn't it? Yes, it is. Let's center this bad boy. Boom. Okay, so the radius is A. Hopefully you can see that. If you're just looking down on the xy plane, we've got this lovely little circle. Okay, so that means the base region, theta, is going to be bounded between 0 and 2 pi, and r is bounded from 0 to a. Now, but what about the height of the solid? Well, the sphere, you could just use that same ray trick. It's in the z direction that we get the height of the solid. It enters at the lower half of the sphere, and it exits at the upper half. Okay, so what's the equation of a sphere centered at the origin, radius A? Well, let's think. It would be x squared plus y squared plus z squared equals a squared. The height, I have to solve for z in terms of x and y, but let me just make them r squared already, right? So z squared is a squared minus r squared. Z is plus or minus square root a squared minus r squared. The upper half of the sphere would be the positive radical, a squared minus r squared. The lower half is the negative radical, negative a squared minus r squared. So there you go. We're ready. Sphere of radius A will have volume 0 to 2 pi, 0 to a, top, rad a squared minus r squared, minus bottom, negative rad a squared minus r squared. And then I need r dr d theta. This needs to move immediately. R dr d theta. Are we all right? We're great, Professor V. Oh, good. Okay, this is going to give me 2 of the same. So let me take a 2 outside. You know what? I don't see a single theta. So this is going to go bye-bye. I'm going to slap a 2 pi on here. And then we have 0 to a radical a squared minus r squared r dr. Okay, perfect. Was that too aggressive? No? You're all right? Now, I'm not going to actually do the u sub, but what you could do is you're going to let u be a squared minus r squared. Then du, remember a is a constant, would be negative 2r dr. All I have is r dr. So when I take the antiderivative, I'm going to pick up a negative 1/2. And then remember, all of this is a squared minus r squared raised to the positive 1/2. So when you take the antiderivative, You add 1 to the exponent, so it would be to the 3/2. We divide by the new exponent, and then I'm going to add that negative 1/2 from the u sub that I didn't actually do, but I know it's there. And then I still have this 4 pi outside. And then this is all going to get evaluated from 0 to a. So that's how you integrate in Calc 3, really slick. If you need to write out the first few steps of the u sub to just see what constant you're going to pick up as a result of doing it, I would say, yeah, that's a good move to make. But you don't want to actually go through all of it because then you have to technically change your limits of integration and whatnot. And hopefully at this point, you're slick enough, you know, this is all to the 1/2. Add 1 to the exponent, divide by the new exponent. This was from the u sub, and this has been hanging out minding its own business. Okay, I just want to help you guys really step up your integration game on stuff like this. Okay, then we have out here just a cute little negative 4 pi over 3, right? Because those 2's cancel. And then I have, so if I plug in a for r, right? A is a constant. Yes, yes, yes. We have a squared minus a squared to the 3/2 minus a squared minus 0 to the 3/2. Okay, so this is gone. And then these negatives cancel. So we have 4 pi over 3 times a squared to the 3/2. Well, that's 4 pi over 3a cubed. Which, isn't that the formula for volume of a sphere? Radius A? It certainly is, guys. It certainly is. Okay. More. Find the volume above the cone, z equals rad x squared plus y squared, and below the sphere, x squared plus y squared plus z squared equals 1. We certainly need to find the intersection. We have to. You can do it before or after you switch to polar. It's really up to you. I'll just leave it like this. So easiest thing to do, this is just the half cone, right? We know like a full cone when you studied it in the beginning. It's all of this, yes? But when you only have the positive radical, then we're looking at just the upper half of the cone. Let me square both sides because then you know what? Oh, so cute. If z squared is x squared plus y squared, then I can replace this x squared plus y squared with another z squared. So I've got z squared plus z squared is 1, 2z squared is 1, z squared is 1/2. So z equals plus or minus 1 over rad 2. That also corresponds to, that's right, z squared is also x squared plus y squared. So x squared plus y squared is 1/2. So basically they intersect in the circle whose radius is centered at the origin, and radius is 1 over rad 2. I misspoke, excuse me. Okay, so let's graph that. This is the intersection right here. Let me just draw it in the XY plane and then we could put together a 3D picture. Don't worry, we got this. So here's the circle. Just don't forget the radius is 1 over rad 2. 1 over rad 2. I would say that's the biggest mistake students make is sometimes they forget to take the square root of the constant. I know it sounds silly, but it truly is. So this 2D region will determine our limits of integration. And thankfully it's going to be relaxing. It's just going to go 0 to 2 pi and r is going to go from 0 to 1 over rad 2. I really wouldn't rationalize the denominator. Not until maybe the very end if you need to, okay? Because sometimes when you square these things, 1 over rad 2 is much easier to square than rad 2 over 2. So my goodness, it doesn't make life better. 3D graph time. Above the cone, below the sphere. Above the cone, below. So since it's only the upper half of the cone, it's only going to be the upper half of the sphere as well. Yes, did you pick that up? It's not a full sphere like in the last problem. They intersect when z is 1 over rad 2. Okay. But the sphere's radius is 1. Okay. So this is where they intersect. This is like the little purple region that I showed. The sphere's radius is bigger. It's 1. Okay, so let me draw the sphere. Let me do this color here. Here's the sphere. Oh, that looks so lumpy dumpy. Hold on. And then the cone's gonna intersect it like right around there. Let me make this magic happen. Boom. Here's the cone. Oh yeah, that looks so good. Okay. And then that's why we found that the intersection was right here. Here's this little purple selection that we have graphed over there. Okay. Sorry guys, this is a little wonky. It's not my best work, but it's okay. Hopefully you get the idea. Above the cone, below the sphere. Above the cone, below the sphere. So above the cone, below the sphere is this part. It looks like an ice cream cone. Yes? Okay, cool. So I need the height of the solid. The height of the solid is going to be in the z direction. So you go like this. Here's a ray in the z direction. Where it hits the solid first is my lower bound. Where it hits the solid second is my upper bound. Okay, you could think we're doing again like top minus bottom. So on the top is the sphere. Sphere. On the bottom is the cone. Sphere minus cone. But they need to be in polar. Oh me, oh my. Okay, so here's the sphere. X squared plus y squared plus z squared equals 1. So z squared is 1 minus x squared minus y squared, which is 1 minus r squared. Only top half. So z is rad 1 minus r squared. That's my sphere. And then the cone here, that's z equals rad r squared. We're only in the top half, so absolute value of r is positive r. So it's going to be rad 1 minus r squared minus r. You got it? Okay, here we go. Volume. 0 to 2 pi. 0 to 1 over rad 2. Sphere minus cone. Rad 1 minus r squared minus r. r d theta. I don't see any thetas, so we're going to slap a 2 pi on here. And then let's distribute 0 to 1 over rad 2. R times the square root 1 minus r squared dr. We're going to do the same shortcut. Are you ready? I'm not going to use sub. We're doing it in our head. Had we used subbed and let u be 1 minus r squared, here, I'll write the first few steps out. If u is 1 minus r squared, du is negative 2r dr. All I see is r. So that would be negative 1/2 du is r dr. So you're going to pick up a negative 1/2 from the u sub that we didn't do. This is all raised to the 1/2 power. So antiderivative will have that quantity raised to the 3/2. Then we divide by the new exponent. Then we're done. Yep. Minus antiderivative of r squared, 1/3 r cubed. And then evaluate this from 0 to 1 over rad 2. It's really nice when you get good at doing this, because notice this term didn't need the u sub. So if you were going to actually write it all the way out, you'd have to split this into 2 integrals. Who has time for that? Who has time for that? Not me. Anyways, this is going to be a fun exercise in seeing how well you can simplify radicals. I'm not going to work through it. I'm just going to let you see how on point your algebra is. You better end up at pi over 3 times 2 minus rad 2, okay? If you're on the struggle bus and you can't get there, let me know. I think you guys should handle it, though. You're in Calc 3 by now, okay? Good, good. Inside both the cylinder, that word both is crucial. Both the cylinder, x squared plus y squared equals 4, and the ellipsoid, 4x squared plus 4y squared plus z squared equals 64. This is a cylinder because z is missing. So we basically have that circle of radius 2 in the xy plane projected up and down forever in the z direction. It's an infinite cylinder. And then it's going to slice through the ellipsoid. So we want the area inside, or the volume, excuse me, not area. We want the volume inside both. So like your ellipsoid is like, I'm going to draw a deformed one really quick. And then the cylinder comes through like this, right? Forever. So we want basically this, you know, inside both of them. Okay, that looks disgusting. We'll draw something better in a moment. Don't worry. I just wanted to give you a general idea of what's going on in your head. Well, we ought to find the intersection, right? Yes. So x squared plus y squared equals 4. That's definitely going to be my base region over which I'm integrating in the xy plane. I don't even know if you need to graph it. We could see theta is going to go 0 to 2 pi and r is going to go 0 to 2. I just need to figure out upper bound and lower bound, right? Maybe you can tell it's just going to be top and bottom of the ellipsoid if you solve for z. I don't know. Let's figure out the intersection though. Let's be proper. So x squared plus y squared equals 4. If I take a 4 out here, x squared plus y squared plus z squared is 64. You see that? And then I can replace this with 4. Nice, huh? Okay, so that's 16. So then z squared is 48. So z is 4 rad 3 and negative 4 rad 3. Top and bottom. So, I mean, how seriously do we want to graph this guy? Not too seriously, Professor V. Okay, good. Because I didn't set it equal to 1. It's going to bother me though. Let's divide everybody by 64. So we have x squared over 16 plus y squared over 16 plus z squared over 64 is 1. I just want to draw it nicely. I do. Okay. That looks disgusting. Hold on. Okay. You guys, I'll have you know, I sacrificed going to hot yoga today to make this video. I hope it's helpful. 4, 4, 4, 8. How much is 4 rad 3? I wonder. 4 times 1.7. Give me a minute. Because I just want to know how high to draw this intersection. Oh no. Okay, here we go. Rad 3 times 4 is about 6.9. Okay, I just wanted to know that. All right, thanks guys for giving me that. So here we go, ellipsoid coming in hot. Oh God, that looks disgusting. Hold on. Looks like an egg, very much. Okay. Then the cylinder will come through and intersect. Remember, the radius of the cylinder is only 2. And I didn't draw it because we knew so easily what it would look like. Yes. Okay. Very nice. It's going through forever. Yeah? So this is kind of where, this should be my 4 rad 3 right there, where they intersect on the z-axis. And then down here, that's kind of your negative 4 rad 3. I guess, finding that wasn't essential because we want the volume of all of this as well. It doesn't really, we're not cutting off where they intersect. So we didn't really need to know that except for just labeling our graph, okay? Had they said they wanted it only inside the cylinder, not also that, then maybe you would need to find that height in z, but it was not important. Okay, so we've got the base region set up. 0 to 2 pi, 0 to 2. Now I need to figure out what's the height of my solid. So we need top minus bottom. And then again, it's moving in the z direction. So bottom half of the ellipsoid, top half of the ellipsoid. Bottom half, top half. Okay, well here's my ellipsoid. Z squared equals 64 minus 4x squared minus 4y squared, which is 64 minus 4r squared. Top half is the positive radical, bottom half is the negative radical. It's going to end up being doubled. Can you see that? Because you're going to have positive rad 64 minus 4r squared minus negative rad 64 minus 4r squared r d theta. Okay, good. So then this ends up being doubled. I don't see any thetas. Woo-hoo. Add a 2 pi. Then we have 0 to 2 rad 64 minus 4r squared r dr. Again, we're not u-subbing. We're doing it in our head. If u was 64 minus 4r squared, du would be negative 8r dr. So we're going to pick up a negative 1/8. That's it. Yep. So we've got 4 pi, negative 1/8. 64 minus 4r squared will now be to the 3/2, and you have a 2/3 out front. Evaluate this from 0 to 2. See, it really makes it so nice. Okay, what is this going to be? Are those constants correct? Yeah, we're fine. I did it a little differently last time and then it was tripping me out. Okay, this cancels. This is a 4. That's gone. I simplified under the radical last time. I guess that might have helped. It's fine. So this is, oh, and this 4 cancels as well. Great. Negative pi over 3 times, this is going to be 64 minus 16 to the 3/2 minus 64 to the 3/2. Okay, so negative pi over 3. That's 48 to the 3/2, is it not? Minus 64 to the 3/2, that's going to be 8 cubed. So 8 cubed is going to be 64 times 8, which is 512. Oh, wow. Okay. Was that necessary? Then 48 to the 3/2, I would break it up because 48 is 16 times 3. So 16 to the 3/2, that's going to be 64 times 3 to the 3/2, that's going to be 3 times rad 3, and then minus 512. Negative pi over 3 sitting out here. So 64 times 3, that's 192. Rad 3 minus 512. And I believe we can factor out an 8 from both of those guys, right? So then this is going to be 24 rad 3 minus 64, negative 8 pi over 3. And then reverse the order of subtraction. We don't need that disgusting negative. And then 64 minus 24 rad 3. That was certainly the worst one of the video, I think. Just evaluating and cleaning up. Okay. Last couple are super fun. Easy breezy, I promise. If you see these on an exam, you should rejoice. Evaluate the iterated integral by converting to polar coordinates. So right now, these are set up in the Cartesian coordinate system, rectangular, and we're just going to switch it to r's and thetas and then be on our merry little way, okay? Notice here the outermost limits for x tell me that the region D is bounded from 0 to 2, and then y is bounded from 0 to rad 4 minus x squared. We know this is upper half of a circle, right? Top half. Circle with radius 2. So maybe you don't even need to graph it. Maybe you don't. But you know what? We will. Because we don't take chances. What if in your haste you make a careless error? That would be tragic. It really would for your grade. Oh, the tragedy. Okay, here we go. Radius is 2. Top half of the circle. But also, x only goes from 0 to 2. So guess what? We're only in quadrant 1. Did you catch that? Because x doesn't go from negative 2 to 2. It goes from 0 to 2. Got to be on your A game, guys. So theta is bounded between 0 and pi over 2. That's it. And r's easy this time. Just 0 to 2. 0 to 2. 0 to 2. Perfect. Time to switch to polar. Theta goes on the outside. I want to say always. God, can I think of a time theta wasn't on the outside? Not really. Okay, r goes from 0 to 2. This is going to be e to the negative r squared, and then instead of dy dx, r dr d theta. Then you evaluate this integral, pi over 2, 0 to 2, e to the negative r squared r dr, yada, yada, yada. You should get pi over 4 times 1 minus e to the negative fourth. Nice? Great. Last one. I'm so sad. This was such fun. Okay, integral 0 to 1/2. Lower limit, rad 3 times y. The y is not under the radical if that's not clear. To rad 1 minus y squared, xy squared dx dy. Okay, so outermost limits are for y. Y goes 0 to 1/2. X goes from rad 3y, what the heck, to rad 1 minus y squared. Oh, okay. So this, hopefully you're comfortable, right? This is the right half of a circle. Yes. With radius 1. What is this x equals rad 3y business? What is that? Okay, don't be scared. X equals rad 3y. You don't like it. Solve for y in terms of x. Maybe you'll feel better. Y equals 1 over rad 3x. This is a line, guys. Don't freak out. The slope is 1 over rad 3. And I told you tangent of theta is that slope. So what's theta? When is tangent 1 over rad 3 at pi over 6? That's important. So here we go. We have a circle and it's being cut. Oh no, why must we cut the circle? XY, circle. Cute. We're only looking at the right half of the circle. Okay. And, hold on, we're cutting it with the pi over 6 line. We certainly are. Pretend this is pi over 6. Okay, we're cutting it. So let's see. Let's see, make sure. This is the bound on the left. The circle is the bound on the right. Left to right. Like if you're moving in the x direction, let me erase this highlight. If you're moving in the x direction, that should that should bound the region on the left, and the semicircle bounds it on the right. Left, right. Got it? Okay. So it's just going to be this little wedge here. Just a cute little wedge. Why did they tell me y goes from 0 to 1/2? Because that's precisely where this intersects. This will be at 1/2. This is at y equals 0. Okay? So can we write the bounds now in polar instead? Of course we can. So theta is going to go 0 to pi over 6. Love it. R. What was the radius of this circle? 1. So r goes 0 to 1. That's it. Okay. We're fine. Look at us. Let me just write it out here. That way you can see what the integrand was. Yes? So 0 to pi over 6. 0 to 1. In polar, x is r cosine theta. Y squared would be r squared sine squared theta. And then dx dy, we switch to r dr d theta. Okay, so my limits are all constants, and then I can break up the integrand into a function of theta times a function of r. I'm going to do that down here, okay? So we have some room. So you can write your integral now as 0 to pi over 6 sine squared theta cosine theta d theta times integral 0 to 1 r to the 4th dr. That's an easy u sub. U is sine theta. There's my du staring at me in the face. So it's going to be 1/3 sine cubed theta evaluated from 0 to pi over 6. And then this is 1/5 r to the 5th from 0 to 1. And you should get 1 over 120. Okay, guys. That's it. I promise. I just wanted to do my due diligence and make sure whoever requested the video felt like they could handle almost any double integral and polar that came their way. Do you feel that way now? I hope so. Okay, if you found the video helpful, please give it a thumbs up. Please subscribe. Please share my channel with other people. I hope it grows. It is my dream of all dreams to hit 1 million subscribers or more and to be the #1 resource for students to turn to when they need help in their calculus classes. Okay, like I said, I didn't go to hot yoga so I can make this video because I thought it was so important. I'm going to just ride my Peloton now. I did have a story about not getting good at math by accident. If you want to listen, I'll tell it to you right now. Back in the day, I used to be really into bodybuilding. I even did a few amateur competitions. And the number one thing when I first started lifting weights that frightened me was, I said to my uncle, who's been a bodybuilder his whole life, I said, I don't want to get too big though. I'm a woman. And he told me, nobody gets big by accident. These women that you see, or even men that compete, they've dedicated years. They make intentional efforts. They eat a certain way. They train a certain way. They sleep a certain way. Everything in their life revolves around putting on size because they want to achieve this goal. If you just want to put on a little bit of muscle and you want to just tighten up, you can do that. You will not get big by accident, okay? It does not happen by accident. People put a lot of effort into making it happen. And that's true with anything kind of elite that you want to achieve in life. It won't happen by accident. Even people who are naturally talented at things still work hard when they achieve that real top level of excellence in something. Olympians or athletes who are competing in the World Cup or something like that. You can have natural ability, but coupled with it is years of work, dedication, effort. So the same thing with math. If you want to be really excellent at it, it won't happen by accident. You have to have dedicated, repeated effort and time spent on perfecting this and honing your skills, okay? And some people are naturally maybe a little bit better, but everybody still has to put in the work, all right? That's it. Anyways, if you made it this far, let me know. And I will be back with more content soon. I definitely want to make more Calc 3 videos. So if that's what you're looking for and there's certain sections that you need more examples on, like this one, let me know because I'm happy to oblige. All right. I love you guys so much. Bye-bye.